Thank you for coming to the second portion of our three-part webinar series. Last week, for our collaborative design session, we learned how the teams of HRC divided up the Polaris robot project for team members to complete this complex object delivery design change. Since all of our team members are in completely different locations, communication is key to a successful project. We heard from Mike, our project manager, how he uses SOLIDWORKS Manage to keep the team on track, log our billable time, and to keep us all in the loop for our accountable tasks. Max took the old Project Polaris lift mechanism and claw in SOLIDWORKS and turned the design around to customize each new part for this specific application. This week, I'm going to take the latest revision and run some analysis on the parts that we are concerned with and validate our designs. After I have validated the design and returned a report back to the team, I will send it over to Chris Ivan, our additive manufacturing engineer, to get some prototypes made. Taking the part from Max, I can see that there were some significant design changes last week to the overall size and material of the part. The original part was machined from 6061 aluminum and was built as a 4-stage elevator. The new lift is a smaller 3-stage setup using smaller components for a smaller payload. Making the lift smaller will increase the robot payload, so we'll have more design weight to lift. Since the payload is not as extreme on the new lift, the smaller part should work, but we need to verify it since the material is also different. One of the challenges to changing the design of a part without doing any sort of analysis is that sometimes the guesswork just does not add up, and the part will become a failure. HRC cannot bear that risk if this product fails in the hazardous environment, because then we would need to send humans inside of the environment to go retrieve the machine, which puts the plant staff at risk. Before we machine, print, or in any way produce a bad part, we want to really take a step back and validate the design so this expensive machine does not fail in the field and expose employees or equipment to harm from the payload. Each lift requires quite a few of those components, so getting the loads wrong is not only a shot to our pride in getting the answer right the first time, it's also expensive, and it takes a lot more time to fix once the robot's already being manufactured. Any delays in this process will hold up needed testing and calibration time on the project. SOLIDWORKS simulation will let me take my part and drop it into a simulation study right away. We will run a static stress finite element analysis, or FEA, on this part to determine if the part is going to be safe or not in operation. If we look at the original design and the analysis run on the part in the past, we can compare the behavior of the part to the new iteration and try to achieve the same behavior with a different material so we get the same performance. The original part was inserted inside a 2x1 aluminum tube, so the model was simplified to show the expected loading on the part based on previous experiences designing elevators. This design has been heavily iterated upon, but even this change is a departure since it includes 3D printed components and a smaller 1x1 tubing size. With the aluminum counterpart, we can assume the stress calculation here was pretty accurate because we had no part failures from this machine component. If we change the material and rerun the analysis, we can make a material comparison between the maximum stresses and correlate the difference in strengths of these materials for this type of loading case. Once we know the difference in the factor of safety with the old part, we can compare Max's new design using a scaled down load to that of a known 3-stage lift and know if this part would survive in operation. The old part has a maximum stress located here. If we swap the material, the value changes, and the allowable stress goes down since this material is weaker. On the new part, the allowable load has been scaled down. Once we run this analysis, we get this allowable stress, and this leads us to believe that the part should be fine in operation. Just to be sure, we're going to run a fatigue analysis because this loading happens over and over again and not one time like in a static stress analysis. Now that we've used SOLIDWORKS simulation, I can use the reporting function to catalog my results and upload this for the rest of the team to review before Chris goes to manufacture this part. Remember, we want to get this right the first time, and we can iterate as many times as we want to in the software before we try a full production run. I'm going to send some components over to Chris that have already been reviewed so you can see that process as well. Let's hear from Chris Ivan how he utilizes this technology.
Thank you, Robbie, and thank you for keeping this from becoming a trial and error process. Alright, at this point in the project, I will take the part files and get them ready to 3D print. I will go from SolidWorks to the slicing software and then to the 3D printers. First, I need a high quality STL file of the jaws. I have already done this for the linkage, the bolt shield, the bearing block, and the side bearing block. Next, I will bring the files into Eiger. Notice how I created a file folder here. Eiger being the cloud-based slicing software which comes with every Markforged printer. This is a good place to collaborate with my coworkers also, and it's easy to keep organized using the folders I mentioned. In the case of the linkage, I will reinforce it with Kevlar to give it some added strength while keeping a degree of flexibility. Now I am ready to set up my print job. One bolt shield, two jaws, and three linkages. Four, never mind, four linkages. I then send the job to the print queue. This print will take one full day to be complete. Next, I will set up the parts which will be printed solid on the HP Multi-Jet Fusion. I will change the orientation to maximize the strength of the model, taking into account Robbie's sim analysis. For a full lift assembly, I need 12 bearing blocks and 24 side bearing blocks. Okay, I will auto pack the build and see that it takes 3.5 hours to print this job, which is very fast. Since I started the Markforged printer earlier, let's see what it's doing. Here we have the X7 printing using FDM technology. When it's done, it will email me that it has finished so I can let the rest of the team know we have functional parts ready. At the same time, the HP Multi-Jet Fusion is also printing. We see the fusing agent being printed on a sheet of powder and the fusing lamps curing it. This process is very fast. Once done, we can clean the parts and recycle the leftover powder. And here we see the jaw assembly installed from software to hardware. Back to you, Robbie.
Thank you, Chris. Hopefully, everyone could see how we collaborate with this technology, even though we're miles and miles apart. This has been part 2 of the 3-part series. Today, we learned about how to use SOLIDWORKS simulation to do some design verification on a part, and we learned how to take that part file and drop it into a 3D printer and get some quick prototypes done from SOLIDWORKS. So all of this technology talks to each other, and it really helps us get our jobs done quickly. Next week for part 3 on May 20th, we're going to take a look at the electrical design and the technical illustration and presentation portion with Rob and Warren. We hope you guys will join us for that. We're going to go ahead and open it up for any questions now. So we'll host questions for a little bit, and then we'll end nice, short, and sweet today. Any questions?
Okay, Robbie, this is Warren here. Please excuse the noise in the background. I'll mute this. I'm looking to see if we have any questions.
Yeah, Robbie, actually, I see one here. I'll go ahead and
Chris,
take
it away.
Okay, so one of the question is something that I hear pretty often is, do I have to use STL files? Would a step file be enough? Good question. So yeah, it depends on the slicing software each person uses. The large majority of softwares like Eiger, that I was showing earlier, Cura, which is very popular, Astroprint, and so on, do require STL files. Now, that's pretty easy to get also, like every decent CAD package, SolidWorks and all the other ones out there can export to STL. For softwares like NetFab and Materialize, which are high-end slicing softwares, you can import almost any file format, Step, iGesPara, SolidWorks directly, whatever you have. And then we're talking a lot about STL, but there's also a newer file format called 3MF, and that works very often, and most CAD packages can export that. And then 3MF and VRML are usually used preferred for color print, the HP 580. So to answer your questions, generally yes, you do need STL files, but it depends on the type of software you're using.
Alrighty,
And
thank you,
then
Chris.
I have one more. I have one more here. If I can roll in with this one. Why did I print? He says, why did you print those two on two different machines? Well, I printed them on different machines for flexibility. Everything could have been printed in nylon 12, but because we have the two machines available, and one's closer to me and one's closer to Robbie, I printed them on different locations on different machines. Since the HP parts are nearly isotropic in their integrity, the sim results that Robbie did make more sense to print on the HP and to get the most accurate parts. While the strongest parts will be printed on the Mark IV. But yes, everything could have been printed on one printer. We did it because we were able to use both technologies.
Yeah, the HP does a lot better at volume than the Mark II, but there were a couple of little tiny parts inside of that linkage that needed to be able to take a good wallop, so being able to put Kevlar in the middle also made that assembly last a very long time.
Hey guys, I think we have another question here. This one may be for you, Robbie. Can the simulation software be used to test the flow of liquids or gases?
SolidWorks has a product that can do that called SolidWorks Flow Simulation. We didn't show that today during the video, but yeah, SolidWorks Flow Simulation can do liquids and gases. We use SolidWorks Simulation to do a linear static and a fatigue study in this case. So linear static comes inside of SolidWorks Premium, but if you have like SolidWorks Standard or SolidWorks Pro, you can also purchase SolidWorks Sim Standard, which is a pretty cheap package so that you can get into simulation if you want to do it that way. Flow costs a lot more, but it's a lot more complex of a software.
Okay, well, let me see here. All right, we have one more question here. Please feel free to enter your questions. Do I have to buy a printer? Actually, Chris, I think this one is for you. Do I have to buy a printer? I have a few parts I would like to have printed.
No, of course not. We work with a lot of people that work with the service bureau. We actually also print some parts for a fee. So it depends. It really depends. You feel free to contact us, and we'll be able to either I'll be able to either recommend somebody to do the work for you in your area, or we can do it here in Greenville or in Charlotte, and send it to you, or have you come pick it up. There's a lot of flexibility today. There used to be a time when printers were centralized, or not everybody had one, but now it's a lot more flexible. Yeah, so you don't really have to have a printer to do the staging the process that we showed for our team. So if you don't have somebody that can do this particular stage, there's a lot of options out there, and I'll be happy to assist with information for anybody that has the questions about this.
Any more questions?
Well, let's give them a couple more minutes here. I don't see any more. Let's give them another minute, and I think that'll be it. Anyway, I've been a racer.
All righty. Well, guys, thank you for coming again. Hopefully, we'll see you guys on May 20th for the third part of this, and we'll go through the electrical design and the marketing collaboration and technical illustrations portion. So, look forward to seeing that. Oh, did I just get one more?
Okay.
Oh, we got it. All right. Thank you, guys.
Thank you.
Cheers.